This example is going to go through how to find a value to help make a divisibility algorithm. Okay, so we have two expressions here, P and Q, everything's integers. We have to find a value of K so that P minus 7Q is a multiple of 31. So it's given us a starting place to go from, but basically we'd always be looking for a linear combination of these two expressions that is a multiple of the thing we're checking for divisibility of, which would be 31. So we do what it says. We work out what P minus 7Q is. Okay, by substituting in the expressions that we've got. And then we're going to expand brackets because that's kind of what we do when we see this sort of algebra. And then we're going to collect like terms. We're going to collect together the terms of A and then the terms of B. So that gives us 93A. And then we've got 1 minus 7K times B. So 93 is 3 times 31, so that's great. Now this 1 minus 7K, we need it to be a multiple of 31. So let's jot down some multiples of 31. So we've got 0, we've got plus or minus 31, plus or minus 62, plus or minus 93, and so on. So we'll start easy. We'll first of all think, can 1 minus k equal 0, where k is an integer? So 1 minus 7k is 0. Now that would give us that k is a 7, so that's not going to work. Okay, so now let's try making 31. Okay, so that's going to give us 7k is equal to 30, so that's definitely not going to work. So let's try 1 minus 7k is minus 31. So that would give us 7k is equal to 32. So again, that's not going to work. So let's try 62. Okay, so then we'd have 7k is minus 61. No, but what if we do, so 1 minus 7k is negative 63. So I'll move that so you can see it. There we go. So then we'd have 7k is going to equal, is that right? Oh, 62. There we go. That's what I'm after. There we go. So 7k is going to equal 63. Okay, and that works when k is 9. All right, so that's what we can use. So if k equals 9, then p minus 7q is going to equal 93a plus 1 minus 63b. So that's minus 62b, and we can take out 31 as a factor. Okay. So I've just kind of finished off that result. All right, so we do what we think we should do, which is follow the instructions of the question, find out what P minus 7Q is. We substitute in, we simplify, and then we collect like terms. We've already got one multiple of 31. We require this to be a multiple of 31. So then we just go through multiples of 31 till we find an option that gives us an integer value for k. And then just to check, we've put k in there and we've simplified it, and we can indeed take out a factor of 31. Okay, right, let's look at the next part of the question. So once we've done that, we're now going to show that 31 divides p if and only if 31 divides q for this value of k. So let's have a look. So we had k is equal to 9, all right? And let's start with if 31 divides p, okay? And if we think about what we had before, so our expression is p minus 7q, okay? So we know that if 31 divides p, and since 31 divides p minus 7q, then 31 must divide 7q for that to be true. So if 31 goes into p, then we must be adding or subtracting another multiple of 31 in order for it to be true that 31 goes into P minus 7Q. Okay, so this must be true. And now we can use Euclid's lemma. So a HCF of 31 and 7 is indeed 1. So 31 divides Q. Okay, so that was using Euclid's lemma. Right, so we've gone one way from if 31 divides P, then it also divides Q. So let's go the other way. Okay, so if 31 divides Q, our expression has got 7Q in it. And we know that if 31 divides Q, then 31 certainly divides 7Q. Okay, and since 31 definitely divides P minus 7Q, then if 31 goes into 7Q, it also has to go into P. And it's not a multiple of P, so we don't need Euclid's lemma for that bit. So we've gone from if 31 divides Q, then it goes into P. So overall, 31 divides P implies that 31 divides Q and vice versa. Okay, so we've done the proof. Now this question said, show that 31 divides P if and only if 31 divides Q. This value of K. It didn't direct me to any method in particular, so you can use a different proof if you prefer. All right, let's look at the last part of the question. So now devise a suitable algorithm to determine whether 2,045,535 is divisible by 31. Okay, so we always do f of the easy thing that is a power which has a power of 10 in it. So f of P is equal to Q. So that if we have a number in this format and we turn it into a number in that format, then if 31 divides this one, then 31 must divide that one. And then if we take that number and rewrite it in this format, 31 divides this one, it must also divide that one. So that's the basis for our algorithm. So we're going f of 100a plus b is equal to a plus 9b. Okay, so that's what we're going to use. So we've got f of 2,045,535. So we'd write that as f of, and we go all the way up until the hundreds column. So 2,045,5 times 100 plus 35. We've now written this number in that format. Okay, these are equal numbers. So using my function, I can then write that as this first number, 20,455, plus 9 times 35. Right, so I'm going to do that on my calculator. Oh, sorry, there we go. So 20,455 plus 9 times 35. So 20,770. Quite a big number, but at least it's still smaller than the 2 million one. Okay, so now we take this one and we're going to write it in the format 100a plus b. So what have we got? 207 and then times 100 plus 70. And we're going to now write it in the format of Q. So we get 207 plus 9 times 70. So again, just doing that. So that gives 837, somewhat smaller. So let's try again. So f of 8 times 100 plus 37 is going to be 8 plus 9 times 37, which is 341. Let's try again because that's still quite big. So f of 3 times 100 plus 41. Hopefully this is still better. Where are we? So that'll be 3 plus 9 times 41. Oops. Okay, so that gives 372. So that isn't any better. So let's just see if 31 goes into, for example, 341. So we'll just do that by just normal division. Okay, so 31 goes into 34 once, remainder 3, and then 34 goes into 31 once, so it's 11 times. So 11 divides 341, which then, if we follow it back up the tree, 31 divides 341 as well, then that tells us that 31 divides our 2,045,535 as well. Okay.